All right, so our next AP Chemistry topic is periodic trends. So let's go ahead and jump in and talk about periodic trends. Periodic trends, of course, are related to the electron configuration, which we just learned about. My computer is refusing to cooperate. Okay, there we go. So periodic trends are related to the electron configuration. So let's go ahead and jump in and talk about how where the electrons are determines their reactivity. So first, let's just quickly review a couple of terms. The first one is valence electrons. This should already be very familiar to you, but valence electrons are those electrons that can be lost, gained, or shared in the formation of chemical compounds. Usually these are the electrons that are located in the incompletely filled main energy levels. That's the S and the P block. For transition elements, that means the electrons in the S and the D sublevels. Again, for main group elements, those are the electrons in the S and P sublevels. For transition elements, those are the electrons in the S and the D sublevels. And those valence electrons are really what's responsible for the reactivity of the elements. So, a couple of terms that we glanced over in Honors Chem, but we'll want to make sure that we thoroughly understand for AP Chemistry. The first one is this term effective nuclear charge. So if we have an atom that has more than one electron, which means everything besides hydrogen, electrons are attracted to the nucleus, but they're also being repelled by all the other electrons. So the charge that an electron experiences, we call this effective nuclear charge, depends on both factors. It depends on that attraction and on that repulsion. So we determine this key term, effective nuclear charge, by subtracting this screening constant or shielding constant from the atomic number. That screening constant is usually close to being the number of inner or core electrons. So what that means, and this is important, is that as we move across a period, the number of inner electrons doesn't change, but the number of valence electrons does. So this means that as we move across a period, the amount of shielding or screening does not change, but that atomic charge or atomic number does. And so as we move across a period, effective nuclear charge increases. And we use this term shielding to talk about the repulsion effect of those inner or core electrons. Okay, so now we can start talking about the trends. The first trend we're going to talk about is atomic radius. So first we have to define what we mean by atomic radius. And so we define the atomic radius as half the distance between the nuclei in a covalently bonded diatomic molecule. This is mostly defined this way because it's really difficult to measure the radius of an atom, but it's relatively easy to measure the distance between two atoms. So as we move across a period, the radius is going to decrease. Even though we are adding more electrons and more protons and more neutrons, radius is going to decrease. Atoms get smaller as we move across a period. Why is that? This is because the shielding stays, as we talked about, relatively constant, but the atomic number increases. And so we have an increased effective nuclear charge. As we go down a group, however, nuclear charge is increasing, but shielding is also increasing. And we're also adding more energy levels. So each row on the periodic table adds a shell or an energy level to the atom, and so radius increases as we move down a group. Okay, so this is just a quick graph. You can see as a function of atomic number that atomic radius decreases as we move across a period. So you can see this is all in the same period. and you can see that radius going down. And then it jumps up as we move to the next energy level. So as we move down a level on the periodic table, it jumps up, and then it's going to slide down again. Now I bring this up, this is important. You guys see that there's this little bit of an uptick here, and then it drops down again. This is as we're increasing repulsion. So this is a general trend, generally trending downward. There are a few little exceptions that you need to make sure that you're able to discuss. And then the other piece, now we're in period 3 and you start to get into transition metals, and you notice that those stay relatively constant, and then we have this little jump up. And the reason we have this little jump up in atomic radius as we move across the transition metals is because we're now adding additional electrons to orbitals that already each contain 1. And so the repulsion does increase just that little bit. Okay, so here's our table of atomic radii, same information, just presented in a different format. Again, you notice that in general, it's decreasing as we go across a period. Okay, so you should be able to identify this trend. You have to know that it decreases as we move across a period and increases as we go down a group. You also need to be able to explain why, and you need to use the idea of shielding and attraction in order to do that. Okay, let's talk, before we get into the next trends, let's talk about ionic radii. So when atoms form ions, when they form cations, we know that they lose electrons. They still have the same number of protons, so they still have the same charge, but fewer electrons pushing one another away. And so the radius of cations is actually much smaller than the corresponding atom. So the ions formed by most metals are smaller than the original metal. We talk about that as the parent atom. Anions, on the other hand, are those negatively charged ions that are formed by gaining electrons. So now we're adding electrons, we're adding repulsion, but we're not adding any protons, so we're not adding any more attraction. And so anions are actually larger than their parent atoms. So there's definitely a difference here in ionic radii. So if we look at these ions, you can see that all of our cations are much smaller and all of our anions are much larger. Pretty simple and straightforward. Okay, now let's continue with our discussion of periodic trends, and we're going to take just a quick break to talk about this concept called Coulomb's law. And Coulomb's law is the law that governs the attraction of two charged bodies for one another. And the formula for that law is that it is the product of the two charges divided by the distance between them. And so that means that that attraction is greater when we have greater charge and smaller when we have larger radii. So we'll also talk about Coulomb's law as we talk about these next trends. Okay, so ionization energy. We define ionization energy as the energy required to remove an electron from an atom. So you notice that we are very specifically, when we talk about ionization energy, talking about forming cations. So this is always the energy required to remove an electron from an atom. Ionization energy increases for each successive electron that we take from the same atom. So if we start with calcium, it has 2 valence electrons. Those are the electrons that are available to be removed. The first one that we take off doesn't require very much energy. The second one that we take off is going to take significantly more energy. And now when we get to the third one, okay, because we are changing energy levels and therefore we are changing the radius drastically, there is a huge increase. Ionization energy also tends to increase across a period because as that radius is getting smaller, It gets harder to remove the electrons. Electrons in the same quantum level don't shield as effectively as those electrons in inner levels. There are some irregularities when we have half-filled sublevels. So when you have a half-filled, say, p orbital, if you add one more electron, so now you have 4 electrons in that p sublevel, that paired electron that's in one of those p orbitals is easier to remove because there's more repulsion from the other electrons. So you'll sometimes see that irregularity at that particular level. It also tends to decrease down a group as the valence electrons are farther away from the charge at the center, the nucleus. They are easier to remove, so the amount of energy required is less. Okay, so let's talk about this in the context of Coulomb's law. So in the context of Coulomb's law, anytime we make the radius smaller, we're going to increase that attraction, which means we're going to have to increase ionization energy. Anytime we make that radius larger, then we're going to decrease that attraction and we're going to decrease the ionization energy. Okay, so we've talked about all of this already. Not sure why I have another slide. Sorry about that. Okay, so first ionization energies. When we talk about ionization energy trends, we're almost always talking about first ionization energies. We will be talking about first and second and third ionization energies as we move forward. But when we talk about ionization energy as a trend, we're talking about first ionization energy. And so you notice as we go across the period from hydrogen to helium, there's a big jump. And then we move down. So in period 2, much less energy to remove the first electron from lithium than to remove the first electron from helium. Here's the irregularity we were talking about, where you're going from a fully filled orbital to an only partly filled orbital. And again, that irregularity from a half-filled orbital to a more than half-filled orbital. But in general, the trend is upward. More ionization energy as we go across the periodic table. These flat areas, when we talk about transition metals, because their radii are very similar, their ionization energies also tend to be very similar. So in general, ionization energy increases across a period and decreases down a group. Okay, let's talk about electron affinity. This is the energy change associated with the addition of electrons. So now we're talking about forming anions instead of cations. As we would expect, as we add more protons to the nucleus and don't change shielding, this affinity tends to increase across a period. It tends to decrease as you go down in a group. Those electrons that are farther from the nucleus, less nuclear attraction, meaning that there's less attraction to pull that electron in, less energy released, lower electron affinity. Again, there are some irregularities in the p orbitals, especially when we reach that half-filled or completely filled. But in general, as we go across the periodic table, electron affinity increases. As we go down a group, electron affinity decreases. So this trend and the ionization energy trend are the same. All right, one more term, electronegativity. We remember this is a measurement of the ability of an atom in a chemical compound to attract electrons to itself. So this is its strength in drawing electrons towards itself in a covalent bond. This also tends to increase across a period with that increased effective nuclear charge, decreased radius, and so the product of the charges divided by the radius is going to be larger, so our electronegativity is going to tend to increase. It tends to decrease or occasionally stay the same as we go down a group. Those electrons are farther from the bonding atom's nucleus. Okay, and there are some values for the periodic table of electronegativities. It's important that you guys know that when we talk about electronegativity increasing across the periodic table, we are excluding the noble gases because they don't really very often form covalent bonds, so they're excluded from this category. The most electronegative element on the periodic table is fluorine, and it is assigned an electronegativity value of 4. Okay, across the table, electronegativity increases. Down the table, electronegativity decreases. So this looks just like the ionization energy trend and the electron affinity trend. So it's important not only that you know the trends, but that you can explain the trends in terms of effective nuclear charge, shielding, and Coulomb's law. So as we move across the periodic table, because shielding stays relatively constant, effective nuclear charge increases. As we move down the table within a group, because both nuclear charge and shielding are increasing, effective nuclear charge stays relatively constant, but radius increases. And so since Coulomb's law is the product of the two charges divided by the radius, as radius increases, that attraction decreases. As charge increases, that attraction increases. So make sure that you can explain the trends as well as identify the trends. As always, if you have questions, let me know. I'm happy to answer.